All right, so it is time to start a new section. We've been studying related rates, and now we've come to the last section in chapter 3, section 3.8, about something called Newton's method. So Newton's method is just one example of a type of method, something called a numerical method, which is basically like a way of trying to solve an equation that is not just a direct algebraic solution. Instead, what we're going to do is we're going to approach solving an equation by essentially guessing what the answer might be, and then doing some calculation which will improve that guess. And then we'll repeat that calculation on the new guess and improve it even more. And what you end up getting is sort of a sequence of approximations, which by iterating a certain calculation with those guesses, the sequence of approximations like converges on the actual solution to the equation. And gets closer and closer to it. And the more times you repeat the iteration, the more times you repeat the calculation, the more accurate your approximation of the solution becomes. That's called a numerical method for solving an equation. So let me show you what I have here. I have a Desmos thing here that's going to demonstrate that method. So I have here graphed a function. F of x is 1/10 x squared minus 1. And what we're going to try to do is solve the equation f of x equals 0, which means we want to know where like the x-intercepts are. So Desmos is giving me those answers. And actually, we're just going to look at the positive one over here. So Desmos is telling me that the answer is 3.162. Have you ever wondered how your calculator and how Desmos, how are they able to actually solve equations so fast? Like, how are they actually doing it? What is the program that runs in the background that is calculating the x coordinate of this x-intercept? And the answer is that it's probably some kind of numerical method. It might use calculus. It likely uses calculus. But it's probably not solving an equation in the traditional sense. It's making a very good approximation of that solution, so it can tell us the first 3 or 4 decimal places with high accuracy. So Newton's method is just one example of this type of strategy. All right. So here's how it works. We're going to start by making a guess, and that guess could be really bad. So here is my first guess. It's called x1. You can look at the label on the diagram over here. X1 is our first guess, and I'm going to start that out at 30. So obviously that is nowhere near the correct answer, nowhere near the correct x-intercept over here, but that's okay. We don't need it to be a good guess. So then what we're going to do is we're going to look at the point on the graph of the function for that x value, and we're going to find a tangent line to that function. So pow, there's the tangent line. So the idea is that that tangent line, like the function should be sort of curving towards the x-intercept kind of. And so if we look at where the tangent line is going, where that tangent line where that crosses the x-axis, that should be a better guess than our initial guess. So what we do is we then take that x value where the tangent line crosses the x-axis, which is essentially like a 0 of the tangent line equation. That will be our next guess, x2. And so that should be better than the first one. And then we repeat the process. So what was the process? Find the point on the graph of the equation that corresponds to that x value, and then calculate the tangent line, right? And then look at where that tangent line crosses the x-axis. So that value is our x3. Repeat. Look at the point on the curve, make a tangent line, look at the x-intercept of that tangent line, and that is the next guess, x4. All right, look at the point on the curve, make a tangent line, and look at where that tangent line crosses the x-axis, and that is x5. So now we have x1, x2, x3, x4, x5. And these points are getting successively closer and closer and closer to the x-intercept that we want. But if I zoom in on that x-intercept, I can see that actually I'm still pretty darn far off. Like that's the value, and my x5 is pretty far away from that value. And that x5, by the way, that x value, if you look down here, over here on the side, that's 3.383897, blah, blah, blah. So it's pretty far away from the 3.1623. But that's because well, for two reasons. One reason it's far away is because my initial guess was super far away, right? Another reason it's far away is that I only performed the iteration. I only iterated the calculation 5 times, or 4 times technically. And if I kept going, you can imagine that this point, the next few points are going to get closer and closer and closer. If I did this enough times, which a computer is able to do very easily, then I would get much better. So let's see though what happens if I make my guess better. If I bring my guess closer, you can see everything kind of zooming in. And now with my guess at about 15, if I zoom in on that, on where that green one is, that's pretty close now. And if I look at the value of the green, it's 3.1674. So again, that's getting closer. If I make a really good guess, zoom out. If I make a pretty good guess, like let's bring this all the way down to like 5. Now let's see how close the green dot is to the actual graph. Wow, I can't even see it. Okay, there's the blue one. Where's the green one? Wow. Okay, I have exhausted Desmos's ability to zoom in. This is, what am I at? 5 times 10 to the negative 9th. And it looks like that is very, very close. So what is the value here? It's 3.162277. And the actual value, gosh, what is it? 3.162, 3.1623, 3.16227. I mean, that's pretty close. That's accurate to at least like 3 decimal places. And that is with a guess of 5, which is, I mean, in all respects, actually pretty darn far away from the right answer. And there's only 5 iterations of the method. So what we're seeing is it converging in on the solution to the equation. Now, if I were to guess too small, like let's say I guess 2, it still works. So we get the first tangent line actually sends me over onto the right-hand side, and then the second tangent line sends me over here, and then the third tangent line, it kind of bounces back and forth a little bit. Let me see if I can demonstrate that a little better. There we go. Yeah, so the first tangent line, red sends me over here, purple sends me there, and then, oh yeah, once it moves to the right, then it just homes in from the right-hand side coming in. Now, I could, though, make my guess too far away. What if I make my guess a negative number? Oh, shoot. Sorry, I need to fix something here. Negative 5. What if I made my guess a negative number? So if I make my guess a negative number, then the particular shape of this graph actually causes Newton's method to start homing in on the other x-intercept. All right. So it's like depending on what your initial guess is, you could end up zooming in on either of the 2 possible solutions to this equation. Okay, it just depends on like the shape. And actually it depends a lot on whether you're on the left or the right side of this like local minimum value right here at 0. Okay. So that's basically how Newton's method works. The idea of making a sequence of guesses that after a few iterations gives you a very accurate approximation. We're going to put that into math now on paper and see what it looks like.